Dear students, after studying this module, you shall be able to know about Hammett equation and its effect on meta and para substituents in the aromatic ring system, to the rate of reaction for many reactions, learn about the applicability of Hammett equation for electrophilic aromatic substitution, familiarize with the reasons for the failure of Hammett equation in case of electrophilic aromatic substitutions, and know about the modified Hammett equation for the same, and also you will learn and identify the selectivity relationship. Let us begin with the introduction of this module. The rates of electrophilic aromatic substitution, also depicted as EAS in the short form, are not same for a set of aromatic ring systems having different substituents and a given electrophile. One always wonders the way in which substituents modify the reactivity of the aromatic nucleus. In order to answer, to certain extent at least, such questions, correlations of reactivity have been drawn in which relative reactivity in different aromatic substitutions can be expressed by equations containing one term characteristic only of the substituent and another term which depends only on the reaction. The best known equation for this is the Hammett equation, which was originally deduced for the benzoic acid ionization equilibrium and defined as log K by K naught is equal to rho sigma. Students, in this equation, K is the rate or equilibrium constant for a substituted compound in a reaction series. K naught is the rate or equilibrium constant for the unsubstituted compound in the same reaction series. Sigma is the log K by K naught for the benzoic acid ionization equilibrium chosen as the standard reaction series, although many substituent constants have been calculated for other reactions as well. K naught is the acid dissociation constant for the ionization of the benzoic acid, and K is the acid dissociation constant for the ionization of substituted benzoic acids. Rho is a dependent variable which is a measure of the susceptibility to substituent effects of the reaction series under consideration relative to that of benzoic acid ionization series. Since log K naught is directly related to the standard free energy change accompanying the ionization of benzoic acid, delta G naught, which is equal to minus 2.303 RT log K naught, and log K is directly related to the standard free energy change accompanying the ionization of the substituted benzoic acid, the Hammett equation is an example of linear free energy relationship. Now, since the K is dependent somewhat on the temperature and critically upon the nature of the solvent which is involved, sigma is defined specifically for water at 25 degrees Celsius. Also, since the magnitude of the substituent effect depends upon the position of the substituent on the aromatic ring, there are different substituent constants for all the positions like meta, para and ortho. It should be noted, students, that by definition, Hammett substituent constants are related to hydrogen as a basis of comparison. That is to say that sigma hydrogen is 0 because it is taken as a standard. The sign of sigma can tell you about the relative effect of the substituent which is on the aromatic ring. If, let us study the cases, if K by K naught is greater than 1, this implies that the substituent has increased the acidity of the benzoic acid, that means sigma is positive. Such a substituent is considered to be an electron withdrawing group because electron density is increased at a reaction site in the product benzoate anion, and an EWG, that is an electron withdrawing group, will favor this change by withdrawing electron density away from the reaction site. Groups such as metachloro, parachloro, metanitro, paranitro, etc., which have relatively large dipole moments oriented with the positive end directed towards the reaction site, are or can be considered as electron withdrawing groups. Let us consider the next case in which K by K naught value is less than 1. It implies electron donating groups are present, that is groups which tend to increase the electron density near the reaction site. They disfavor the ionization to a negatively charged ion. These include the alkyl groups at both the meta and para positions, para-alkoxy groups, para-amino groups. The substituent constant, that is sigma, is a measure of the total polar effect exerted by a substituent X on the reaction center. That is, this is relative to no substituent. Now the reaction constant rho is the slope of the line correlating log K with the sigma values of the various substituents. The sign of the slope tells whether a reaction rate is accelerated or suppressed by electron donating versus electron withdrawing substituents which are present. Negative rho is diagnostic of the development of positive charge at the reaction center in the transition state of the rate limiting step. However, the positive rho value is diagnostic of the development of negative charge at the reaction center in the transition state of the rate limiting step. The magnitude of rho, students, is a measure of how susceptible a reaction is to the electronic characteristic of the substituent. Hammett equation gave fairly good correlations for the effect of meta and para substituents in the aromatic ring system to the rate of reaction for many different reactions such as esterifications, electrophilic addition to phenylalkenes, elimination reactions, nucleophilic substitutions, etc. But this equation failed for ortho-substituted systems, which was attributed to the steric effect of the ortho-substituent on the reaction center. Also, its applicability for the electrophilic aromatic substitution is limited, which will be discussed in the preceding sections by me. Now, let us come down to the next topic, which is the applicability of Hammett equation for particularly electrophilic aromatic substitution. Now, let us first tell you and discuss about the reasons for the failure of the Hammett equation in case of electrophilic aromatic substitutions. For aromatic substitution reactions, quantitative rate studies are difficult as there are usually several hydrogens that can leave, and hence the measurement of overall rate ratios does not give a complete picture as they do in the nucleophilic substitution, where it is easy to compare reactants having only one possible leaving group. Therefore, partial rate factor for a given group and a given reaction is used, which gives the rate of substitution at a single position relative to a single position in benzene. For example, let us consider toluene. Toluene is acetylated at the ortho position 4.5 times as fast as the single position in benzene itself. Therefore, its partial rate factor that is at the ortho position will be 4.5 for the acetylation reaction. Similarly, if the reaction takes place at meta, it will be 4.8. However, at the para position, it is going to be 749. Once partial rate factors for a reaction are known, one can predict the proportions of isomers to be obtained when two or more groups are present on a ring by making the assumptions that the effect of substituents is independent. Now, if one supplies or the Hammett equation for electrophilic aromatic substitution reaction, that means let us apply this partial rate factors to the Hammett equation, we get, that is, original Hammett equation is log K by K naught is equal to rho into sigma. The K naught is divided by 6 and for meta substitution K is divided by 2, so that the comparisons are made for only that very position, that means ortho, meta or para. However, students, while this approach worked fairly well with benzenes containing electron withdrawing groups, it failed for those that contain the electron donating substituents. This failure arises because Hammett's original model reaction, that is the ionization of substituted benzoic acid, does not take account of the direct resonance interactions between a substituent and the site of reaction. For example, consider the resonance structures for electrophilic aromatic substitution of anisole, which is an ether, which shows the transition state to be stabilized by direct resonance with the substituent. Now, since these interactions are impossible when the substituent is attached to the meta position and are not operative even for para, resonance electron withdrawing substituent like nitro or acetyl, the sigma values of these latter kinds of substituents are still valid and they nicely fall onto the standard Hammett plot. Now, we have modified the Hammett equation in certain cases. Now, let us study the modified Hammett equation for electrophilic aromatic substitutions. After the failure of the classical Hammett equation for electrophilic aromatic substitution, it was suggested that by choosing a different model reaction in which the direct resonance effects of substituents contributed, another equation similar to that of Hammett equation might be devised to correlate the rates of electrophilic aromatic substitution reactions. Brown and his co-workers chose a different model reaction, like it was earlier benzoic acid. Now here it would be chosen by Brown and his co-workers the solvolysis of substituted dimethylphenyl carbonyl chlorides, that is also shortly known as cumyl chlorides, in 90% aqueous acetone. It was thought that because a positive charge develops during the transition state, as you can see in this figure, more satisfactory correlations can be made even for electron donating groups and not just for electron withdrawing groups, as we have discussed earlier. In the case of para substituted substrates, the transition state represented by the resonance structures, as we can see here the two structures, is stabilized by direct resonance interaction between the substituent and the site of reaction. Now you can see the two stabilized resonance structures. Now using this data for the new reaction, that is for the solvolysis of cumyl chlorides in 90% aqueous acetone at 25 degrees Celsius, a plot of Hammett's sigma constants versus the logarithms of the rate constants for the solvolysis of a series of meta substituted cumyl chlorides was henceforth plotted. Now you can see the plot we have drawn here in case of the solvolysis of cumyl chlorides in 90% aqueous acetone. As expected, meta substituted cumyl chlorides gave a good linear relationship, while para substituted ones fall out of the plot of the straight line. Brown then modified the Hammett equation as log of ky divided by k naught is equal to rho star sigma star. Now students, as you can see, this is the modified Hammett equation. Here he introduced a sigma plus factor or the sigma star factor. We know it as sigma plus, which were determined by extrapolating the originally outlined points for the para substituted cumyl chlorides to fit into the standard Hammett curve. Now you can see how we had actually extrapolated for the para substituted cumyl chlorides in the original Hammett curve and how we had extrapolated. A look into the sum of these sigma plus values is presented here. Now you can see for the para substituted cumyl chlorides how the value of sigma and sigma plus is varying. See, for NMe2, that is the secondary amines, you can see here to the earlier sigma values were minus 0.3, now it is sigma plus value is minus 1.7. Similarly, for all these values you can see, like for fluorine it was earlier plus 0.34, now it is minus 0.07, so on for all these substituents like ethers, SMe, that is the thioethers, the methyl and the chlorine. For these cases, when sigma plus is used to designate the substituent constant, the reaction parameter should be denoted as rho plus. Rho plus for this new standard reaction is minus 4.5. The negative sign indicating the development of positive charge at the reaction site in the transition state. This modified Hammett equation, students, using the Brown's sigma plus constants gave a fairly correct correlation of the substituent effects on various electrophilic aromatic substitutions. For example, for nitration reaction of substituted benzenes carried at 25 degrees Celsius in nitromethane or acetic anhydride. A plot of K by K naught against sigma plus produced a rho plus value of minus 6.53. Now you can see here for the Hammett plot we have plotted for many values and many substituents this plot. Another example, students, is the Friedel-Crafts acylation reaction. Here also sigma plus values were used for electron donating groups. Linear relationship was witnessed with observed value of rho plus is equal to minus 0.49. Now you can see here how the Friedel-Crafts acylation is taking place and how the sigma plus values are varying for electron donating groups such as OMe, as in here in case of anisole. Now we will talk about, students, the selectivity relationship. Brown has also suggested another modification of the Hammett approach, which is known by the name of selectivity relationship, which is based on the principle that reactivity of a species varies inversely with selectivity. For example, on comparing the reactivities of toluene relative to benzene in aromatic substitutions, these were found to be proportional to the ratios in which toluene underwent para and meta substitution as shown in the table. Now you can see here this table tells you about the relative rates and isomer distribution for substitution in benzene as well as toluene. Now you can see here for bromination, chlorination, benzoylation, nitration, mercuration and isopropylation what are the relative rates and the product distribution and their ratios. This proportionality can be expressed as, that is, log F for the paramethyl is equal to B log F of paramethyl divided by F of metamethyl, where F of paramethyl and F of metamethyl are the partial rate factors for substitution at para and meta positions respectively. Now by defining the selectivity factors SF as SF is equal to log of, that is, F of paramethyl divided by F of metamethyl, and the former equation becomes log of F paramethyl is equal to BSF. This equation is now similar to the Hammett rho plus sigma plus equation. B being a parameter whose value depends on the values of sigma plus for meta and paramethyl groups. Now you can see here that log of F of paramethyl is equal to sigma plus of para divided by sigma plus of para, only sigma of meta, into SF, and log for metamethyl is equal to, again you can see here sigma plus it will be for meta divided by sigma plus of para minus sigma plus of meta. Now here it is sigma plus in this factor into SF. SF is related to rho plus as SF is equal to rho plus brackets sigma para plus minus sigma meta plus. The selectivity factor is a measure of selectivity of an electrophile which is expressed by the extent to which it discriminated either between benzene and toluene or between the meta and para positions in toluene. In simple words, it states that the more reactive is the electrophile, the less is the selectivity towards any particular atom or position of the substrate. Through this relation, selectivity was considered to be related to its reactivity and assumed not to be dominated by other factors. Thus, powerful electrophiles such as those in Friedel-Crafts alkylation reactions were considered to be electrophiles which would be less able to distinguish between substrates and positions than a weakly electrophilic reagent. Thus, the electrophiles operating in reactions which have low selectivity factors or SFs or reaction constant, that is sigma plus, are intrinsically more reactive than the effective electrophiles in reactions which have higher value of these parameters. For example, consider bromination reaction of a set of substituted benzenes with Br plus electrophile would result in lower selectivity than those with relatively less Br2 species. A series of experiments were done by Ola et al. And the effect of substituents on the reactivity and selectivity of electrophile were determined. Some of the data is represented in this given table and the salient points are discussed. Now let us discuss these points. It was shown that substituents may affect the substrate reactivity as measured by the K toluene divided by K benzene, that is, or represented as KT divided by KB ratio. Thus, while electron donating substituent located at position ortho and para with respect to benzylic center increase the KT by KB ratio, electron withdrawing substituents however decrease it. The acylation of toluene and benzene clearly proved the importance of substituents on the electrophilicity of the substituting agent, which was reflected by a high KT by KB ratio. Next point is, the effect of the nucleophilicity of the aromatic substrate was observed to cause similar effects, so that with increasingly more basic aromatics, even relatively weak electrophiles resulted in early transition states resembling more starting materials than those of intermediates. Now here is a table we were discussing, that is the KT by KB ratios for TiCl4 catalyzed, that is titanium tetrachloride catalyzed benzylation of, and AlCl3 catalyzed, that is the aluminum chloride weak Lewis acid catalyzed benzylation reaction. Now here you will see different KT by KB ratios in the catalyzed benzylation and benzylation of TiCl4 and AlCl3, and notice the different values. However, this relationship was found to hold true only under certain cases and under very closely related conditions. It was observed that this treatment worked well with groups such as methyl that are not polarizable. As each electrophile makes a different demand for the electrons in the transition state, with more polarizable groups, the correlations are mostly unsatisfactory. Also, for more stronger electrophiles, this selectivity relationship was found to be very much unsatisfactory. Let us consider an example. The selectivity relationship is found to hold for nitration in sulfuric acid, where the nature and concentration of nitronium ion, which is the electrophile, is well established. However, if you consider mercuration reaction and in Friedel-Crafts alkylation reaction, many times the selectivity relation breaks down. In case of mercuration, it was formulated that reversible formation of a VLAN intermediate takes place on attack by the electrophile, followed by a loss of electron. However, due to the similar rate factors of a reversible step 1 and that of irreversible step 2, the influence of ring substituent is nullified, and so the selectivity relationship does not hold good at all. Now here you can see the mercuration reaction we have shown you. Also, the selectivity relationship was found to be valid only for simple processes where single bond breaking or formation takes place in the transition state. Similarly, reactions in which solvation factors contribute significantly do not obey this relationship. However, in spite of such limitations of this relationship, the empirical reactivity selectivity relationship has been illustrated for a variety of electrophilic aromatic substitution reactions and to other reactions as well, and this provides experimental support to study their mechanisms. Now students, we have studied all the Hammett equations, the modifications and the failures and the selectivity relationship. Now I would like to summarize this module for you. In this module, we have taught you that the correlations of reactivity have been drawn in the form of Hammett equation, in which relative reactivity in different aromatic substitutions can be expressed by equations containing one term characteristic of only one of the substituent and another term which depends on only the reaction. That is, in short, log K by K naught is equal to rho sigma. However, Hammett's approach worked fairly well with benzenes containing electron withdrawing groups, as we have already told you, but it failed for those containing electron donating substituents. Then we taught you that this failure arises because of Hammett's original model reaction, that was for the ionization of substituted benzoic acids, does not take into account the direct resonance interactions between the substituent and the site where the reaction is to be taken place. Now, by choosing a different model, that is solvolysis of cumyl chlorides in 90% acetone, aqueous acetone at 25 degrees Celsius, in which the direct resonance effects of substituents contributed, a modified Hammett equation was formulated which used sigma plus values, was devised to successfully correlate the rates of electrophilic aromatic substitutions. Now, this newly formulated Hammett equation was log K by K naught, that is Ky by K naught, is equal to rho plus and sigma plus. So, instead of K, it is Ky now, which is actually taking into considerations the various effects of substituents also. Now, the scientist Brown also suggested another modification to the Hammett approach called the selectivity relationship, in which we have taught you that it is based on the principle that reactivity of species varies inversely with the selectivity. In short, log F of paramethyl is equal to BSF. The selectivity relationship tells us that the electrophiles operating in reactions which have low selectivity factors, that is SF, or reaction constants sigma plus, are intrinsically more reactive than the effective electrophiles in reactions which have higher values of these parameters. A series of experiments under closely monitored conditions validated the concept of reactivity and selectivity. Although the selectivity relationship was found to successfully correlate reactivity as a function of selectivity in several aromatic electrophilic substitutions, it was found to have many limitations and would usually work in simple processes and under closely related systems.